Hello, good afternoon, students. Yesterday we have discussed some part of the introductory part of the solution chapter, and we came up to expression of types of solutions. Like say yesterday we have seen meaning of solution, solvent, solute, homogeneous, heterogeneous, then mixture, then types of solutions. Then yesterday, during the discussion of the meaning of these two, I put one question. When equal quantities of solute and solvents are taken, then upon mixing, they'll form the solution. In that case, I asked you which should be considered as solute and which other should be considered as solvent. Say so. Why that question has come means, usually in the solution, solute quantity will be little, solvent quantity will be more. This is the usual situation. But yesterday, what situation posed was this: if instead of this, if you have equal quantities, if the quantities of solute and solvents are equal, then upon mixing these two, we'll get solution. In such case, which is solute and which is solvent? This was the question, isn't it? And yesterday I got some answers also. The answers I would like to read. I am very much happy that you people have responded to it. That answer goes like this. That answer is I do not know the name of the student who sent it. See, I read this. It is sent by one of the students. If both solute and solvent exist in equal quantities, the concept of solute and solvent becomes relevant. See, if the quantities of both are equal, then the meaning of solute and solvent becomes less relevant or less important. Okay, let us see. But the substance that is more often used as a solvent is normally designated as solvent. That is water, liquid only. For example, 50% ethanol. See here, students. 50% ethanol and 50% water. If this solution we get, if this solution we have, then in this example, what the student said is, this is solvent and this is solute. Then what further the student says is, in such cases, to check the solute and solvent, boiling point concept can be used. That is, by checking the boiling points, we can come to know whether the substance is solvent or solute. As solute has the boiling point more, that is, solute's boiling point is more than the solvent's boiling point. It means that boiling point of solute is higher and boiling point of solvent is lower. Well, this is the solution that is given. And further, yeah, that's what. Well, I congratulate the work done by the student. I do not, name is not there, but anyway, it's a good work and good effort. See, students, if you interact with the teacher like this, teacher will try to give maximum information. You just keep it up. Okay, let us discuss this. When the quantities of solute and solvent are equal, then the concept suggested by the one of the students is this: if the boiling point of solute is, if the boiling point of one of the substances is more, then that substance can be regarded as solute, and the substance whose boiling point is less, that substance can be regarded as solvent. Okay, let us agree for a moment. It means that concept of boiling point difference can help us to find which is solute and which is solvent. More boiling point substance, or the substance with more boiling point is solute, and the substance with less boiling point is solvent. See, students, it has come based on this experiment. Usually what we notice is, if you take normal water, that is the day-to-day water that we consume, if you take that normal water and heat it, so what we notice is, water starts evaporating and getting into the atmosphere. Then when we continue heating, a stage will come where even a single drop of water also gets evaporated. Then we are left out with small quantity of the dissolved salt in it. So based on this experiment, this concept is derived. See, students, before boiling, this normal water has these two substances. One is water and the dissolved salt. This is normal water. Then which is solute here? Dissolved salts are solute. Solvent is water. Now, upon heating this solution, what we notice? What is evaporating? Dissolved salt is remaining. This simply indicates that boiling point of water is lesser than the boiling point of dissolved salt. Therefore, look at this. When equal quantities of two substances, that is CR students, one is ethanol is taken, another one is water is taken, then the substance whose boiling point is higher, that should be regarded as solute, and the substance whose boiling point is less, lower or lesser, then that should be regarded as solvent. See, students, this concept is holding good, or it may be correct only with respect to some examples. But if you go for mixture of gold and copper, this solution, solid solution, this may not hold good. This may not hold good. That means it has got some restricted applications. Clear? So, in such case, what we do is, we do one experiment here. A small experiment here. See, students here. We take substance A in one container, and we take substance B in another container. Here, quantities of A and B are equal. Then question arises, when these two are mixed, then which is solute and which is solvent? See, students, the usual practice of answering which is solute and solvent is this. Suppose we get here, we get the solution. Here, we get solution AB. We get solution here as AB, either by mixing A into B or B into A. That means there are two ways of mixing or two ways of getting this AB solution. Okay, in the first way, what we have done is, see here, in the first way, what we have done, A is dissolved in B. In this case, see students, our usual practice is to get solution is, our usual practice of getting solution is this. Solute is dissolved in solvent. We hardly practice reverse way. That means solvent is added to solute. So usual practice is solute is added to solvent. Based on that, here A is added to B. It means that this is solute and this is solvent. And in the second case, what we notice? B is dissolved in A. Now, in this case, B happened to be solute and A happened to be solvent. So, here, physical state will not come into picture. Is that clear, students? Yeah, this may be one of the reasons, but you know, the usual practice is this: when equal quantities of substances are taken, the substance which is added into another substance is known as solute, and the substance into which other substance is added is called as solvent. Clear, students? Well, this is the usual method. Okay. Let us not see, questions will not come out of this particular discussion. Let us not involve in this in detail. Simply remember that it is just a common sense discussion. Just remember that when two equal quantities of substances are taken, the substance which is added into another substance is called as solute, and the other substance into which this substance is added, that's called as solvent. Clear? Okay. Let us continue from yesterday's discussion. Yesterday we have discussed that there are 9 possible solutions, are there? How many types of solutions? 9 possible solutions are there, and we have added one more extra information into that, which will come in the next part of the discussion. What is that? Colloid. The difference between these two, solution and the colloid is, one is homogeneous, another one is heterogeneous. Okay. Can you remember that? Which combination will not give colloid? Yes, exactly. What is that? Gas and gas will not form a colloid. Why? Yes, true. What is that? Gas and gas will not form heterogeneous system. It will form homogeneous system. And the condition for a system to call it as colloid is heterogeneous. It should be heterogeneous. Therefore, there are 8 possible colloids and 9 possible solutions. Okay. Now, what we do is, students, see, yesterday we have come across this 1 ppm fluoride ion and 1.5 ppm fluoride ion. Can you remember which is acting as a medicine for tooth? See here, if fluoride ion concentration in the paste is 1%, 1 ppm, then it will prevent the decay of tooth. Decay is not possible if fluoride ion concentration is 1 ppm. And if it is 1.5 ppm, decay will take place. Or, see here, can you remember that particular word? Mottled. That means tooth may change its color or some colored patches or start decaying. It means that concentration, the quantity of fluoride ion, in the solution is of more importance. Is it clear? Therefore, to know the quantity of the solution, we have different ways of knowing the quantity of the solution. Therefore, it's also called as, this can also be regarded as expressing the strength or concentration of solute in solution. We have different ways of expressing the strength of the solution. Yesterday we have seen it. What is that? First one is mass percentage. Then this is mass by mass percentage. Second one is mass by volume percentage. Third one is volume by volume percentage. Then ppm. Then mole fraction. Then molarity and molarity. How many? 1, 2, 3, 4, 5, 6, 7, and 8. We have seen that this normality and the formality, they are not reference labs. And this deals with equivalent weight, whereas molarity deals with molecular weight. This is not there for our syllabus. Therefore, whatever is there for our syllabus, we discuss that. So let's begin with mass percentage. Let us understand what we mean by mass percentage. Mass percentage. It is also known as weight by weight percentage of a solute in solution. Okay. See students, just by looking at this representation of symbol, which type of solution it can represent? Solid in solid, solid in liquid. Yes, this is weight. It means solid. Usually it is solid in solid. Not necessary. Not necessarily it should represent solid in solid, but usually this represents solid in solid situation. Okay, students. Let us take one example and define it, what it is. See here. Say 10% of glucose in, say, let's say 10% glucose solution. This is the statement. Then what does this weight by weight stand for? This implies that 10%. This means that 10, this per is nothing but divided by. Cent stands for century. That means per 100. That means this implies that weight by weight is 10 by 100. Weight by weight percentage is 10 by 100. Oh, this is, if it is to be a percentage, then it should be multiplied by 100. Then what will get? 100 will get cancelled, so we get 10%. What is this 10? This is solute. What is this? This is solute. What it is? Weight of solute. And this is weight of solution. So can we prepare the definition for this? See here. This implies that mass percentage is nothing but weight of solute divided by weight of solution into 100. Clear, students? Look at this. This is weight of solute and this is weight of solution. And one important point that you need to remember is this. This weight of solution is nothing but weight of solute plus weight of solvent. Okay. Now here, this 100 is like this. It has come like this. Here, what is the weight of glucose is given? the solute is 10%, means here it is 10 gram. 10 gram of glucose is dissolved in how much quantity of solvent? See students, let it be x gram, but total should be how much? It should be 100. Then this implies that x must be 100 minus 10. This must be equal to 90 gram. Is it clear, students? See, it means that when this one, weight of solution, this weight of solution must be sum of the weight of solute and weight of solvent. Is it clear? Now look at this. Let's go for another example. Say 5 gram of a solute is found in 50 gram of solution. Then what is its mass percentage? Is how much? Mass percentage is how much? Look at this. What is given? What is given is weight of solute. How much it is? 5 gram. Weight of solution is how much it is? 50 gram. This implies weight of solvent is how much? 50 minus 5 is 45 gram. Now it is for 100%, no? It's for 100. That means 5 gram of solute is dissolved in 45 gram of solvent. Therefore, how much gram of solute is dissolved in? How much? Total should be 100. Then out of 100, this should be here. This should be doubling. This should be double. That means 90 gram of solvent. Therefore, this x will be equal to how much? 5 gram into 90 gram divided by 45 gram. This get cancelled. This will be 2. It means it is 10. This is 10 gram. That means 10 gram of solute is present in 100 gram of solute. So solvent is 90 gram. But if you add this into this, it will be 100. It means that mass percentage is 10 or 10%. So this simply indicates that quantity of solute dissolved in that quantity of solvent, which makes it 100. See, so solute plus solvent should total become 100. This is an important key that you need to remember. Clear? So mass percentage is weight of solute divided by weight of solute plus weight of solvent. That is weight of solution into 100. Is it clear? Now let's go for another unit of expression of this kind of the solution. That is the volume by volume percentage. See, students. Suppose we notice that, before this, we go for weight by volume percentage. Weight by volume percentage. So this implies that, suppose 10 gram of solute is dissolved in 100 ml of solvent. Then the mass by volume percentage is how much? See students, what is the total weight of the solution? Here, this is 100 ml is taken. This is 100 ml. This is 100. And weight of solute is 10. Then into 100. This gives us 10%. If you can remember, see students, in the weight percentage, we have taken this as weight of solute and weight of solvent. Isn't it? And the total was going to be 100. But in this case, it is just weight of solvent. Remember this. This is the main difference between weight by volume percentage and weight by weight percentage. Mass by mass percentage and weight mass by volume percentage. The difference between these two is this. In the denominator, with respect to mass by mass percentage, we take total mass of solute and solvent. Clear? But in this case, weight by volume percentage, in the denominator we take only solvent. There is no question of weight. Clear, students? Therefore, weight by volume percentage is weight of solute per weight of solute divided by total volume of solvent into 100. Clear, students? See students. One more thing. We will take another example. Say 25 gram of sugar is dissolved in 1000 ml of water. Then its weight by volume percentage is how much? Remember this. Is it clear? 25 gram of sugar is dissolved in 1 liter. That's 1000 ml of water. Then its mass by volume percentage is. See students. 25 gram is in 1000 ml. Isn't it? But we want weight of sugar in 100 ml. That means weight of sugar per, that is mass by volume percentage, isn't it? How much it is? Say x is equal to 25 into 100 divided by 1000. So this will be 10 and this will be 2.5 gram. Is that clear? That means 2.5 gram of sugar is dissolved in 100 ml of water. That means its mass by volume percentage will be how much of sugar? 2.5 gram. That by volume is how much? 100 into 100. This will get cancelled. This is 2.5%. That is volume by mass by volume percentage of this sugar solution is 2.5%. Is that clear? The main difference in between mass by mass and mass by volume is the denominator factor. In mass by mass case, we take the denominator factor will be total mass of solute and solvent. But in the case of mass by volume percentage, only volume, total volume is taken in the denominator. The denominator factor will be only volume, solvent factor. Now, let's go for another one. We are saying mass by mass, mass by volume. Then we go for volume by volume percentage. See students. Volume by volume percentage is nothing but. Let us take one example here. It is a little bit crucial here. See students. When 10 ml of solution A is mixed with 10 ml of solution B. What will be the total volume? See here, when, is it visible? When 10 ml of solution A, 10 ml of liquid A is mixed with 10 ml of liquid B, what will be the total volume? Is it 20 ml? See here, students. It may be equal to 20 ml or may not be equal to 20 ml. Then one huge question you may have here. How is it possible? I'm not joking here. 10 ml plus 10 ml of two different liquids put together, total volume may be equal to 20 ml or may not be equal to 20 ml. See here, students, this concept we'll study in detail when we go for ideal and non-ideal solutions. Now, if you happen to have a discussion with any of your friends, then you put this question in: 10 ml of A plus 10 ml of B is how much? Total volume is how much? Then 99.99% of the time, they will definitely say it is 20 ml. Then if you say it may or may not be equal to 20 ml, means they may think that you may be out of mental ordering. But it's not that they are true. It is you true. You are true. Let's look at this. See here. Details of this, why this will be not equal to 20 ml. Details of this we'll see when we go for this ideal and non-ideal solution. Now, as of now, if it is equal, then it is called as ideal solution. See, students, when 10 ml of a solution, liquid A and 10 ml of liquid B is mixed, then if you get the total volume as equal to sum of these two volumes, then the solution is called as ideal. Clear? So 20 ml is correct only with respect to ideal solution, and most of the time the solution will not be ideal. Then what is ideal solution? What is non-ideal solution? All those things we shall see in due course of time. And if it is non-ideal, then non-ideal can be of two types: positive deviation from the ideal behavior and negative deviation from the ideal behavior. See, as you have seen in the gaseous state, positive deviation from the ideal gas law or negative deviation from the ideal behavior. Like that. See, students, if it is positive deviation, the total volume will be, this total volume will be more than 20 ml. See, students, if this solution is not, if the total volume is not equal to 20 ml, then the solution will be non-ideal. In non-ideal, there are two cases, two types of non-ideal solutions are there. One is positive deviation. One solution shows positive deviation from the ideal behavior, and the other solution will say show negative deviation from the ideal solution. Suppose the formed solution shows positive deviation from the ideal behavior, means the total volume will be more than 20 ml. Clear? And if it is showing negative deviation from the ideal behavior, then it will be less than 20 ml. Is it clear, students? Well, by keeping this in mind, this is defined. See here, 10 ml of A is dissolved in some quantity of water, some quantity of solvent, so that the total volume becomes 100. See, students, in a container, some quantity of, say, 10 ml of A is taken. So that into this we add solvent B. How much solvent that you add means the total volume should become 100 ml. Is that clear? Suppose we have here a measuring jar. and here it measures like this. The scale is like this. Suppose this is 100 ml, and you have taken this, into this you have taken 10 ml of air. Then, see students here, suppose you add 90 ml of solvent B, then total volume will not be here if it is non-ideal solution, and if it is ideal, 10 plus 90 will be 100. And in case if it is non-ideal, then 10 plus 90 will be either less than 100 or more than 100. But we want only 100. That means we cannot add 90 ml of B here to 10 ml of A. So what we have to do then? You take A, 10 ml of A you have taken, or any ml of A you have taken. Then to that you have to add solvent, which makes the total volume must become this much. How much is this? 100 ml. It means that if it is non-ideal solution, if the solution is becoming non-ideal, see, making the sum of the volumes equal to 100 doesn't mean that you have added 90 ml of B. Is it clear? You might have added more than 90 ml or less than 90 ml, but total volume will be 100 ml. Is it clear, students? Why this comes into picture? Because of the behavior of solution. If the solution's behavior is ideal, then sum of the two volumes will be 100. If solution's behavior is non-ideal, then sum of the two solutions will not be 100, will not be equal to total volume. So in that case, this volume percentage can be defined as volume of solute divided by total volume of solution, into 100. Is that clear, students? Okay, let's go for its illustration. We will take an example. 10% ethanol. 10% ethanol in water means 10 ml of ethanol divided by 10 ml of ethanol plus X ml of water, so that total will be 100 ml. Total will be equal to 100 ml. Total will be equal to 100 ml to 100. Why we have done like this? When ethanol is mixed with water, it will definitely form non-ideal solution. That is why for 10 ml, if you mix 90 ml of water, the total volume will not be 100. It will be either more or less. Whether it is more or less, it will be clear in due course of time. Is it clear, students? Therefore, in the denominator, what must be there? Total volume of the solution. Clear? Okay. So we have seen here mass percentage, volume percentage. That means when I say mass percentage, it means that it is mass by mass. And when I say volume percentage, it is volume by volume. Mass percentage and volume percentage. Third one is volume by mass by volume percentage. Okay, students. Now we'll go for another term, molarity. See, students. Molarity means number of moles of solute. Number of moles of solute dissolved per liter of solvent. Per liter of solvent. Molarity is number of mole. Better call it as of gram moles of solute dissolved per liter of solvent. See students, you have already come across meaning of mole. Mole means weight divided by molecular weight, or you take atomic weight. Then question arises, what to take? Suppose you are dealing with the substance which is a molecule. Then you take molecular weight. And suppose you are dealing with atom. Then you take atomic weight. But in this chapter, 99% of the time, rather 99% of the time, 99.99% of the time, we deal with molecules, molecular form of the substance, and hence mole invariably means this. Okay? Okay. Therefore, molarity is nothing but gram moles of the solute dissolved in per liter of the solvent. This can be written as, gram mole can be written as weight of the solute divided by molecular weight of the solute into 1 divided by volume of the solvent in liter. Or it can also be written as weight of the solute divided by molecular weight of the solute into 1000 divided by volume of the solvent in terms of milliliter. Remember this one. So molarity is nothing but number of gram mole of this solute dissolved in per liter of the solvent. From this definition only we will get the formula. Now let's use this formula. See students, 4 gram of sodium hydroxide is dissolved in say 500 ml water. 4 gram of sodium hydroxide is dissolved in 500 ml of water. Then what is the molarity of the solution? Molarity of the solution is, see here, now we notice weight of solute is how much here? 4 gram. Then weight of volume of solvent is how much? 500 ml. Say students. Then what do we need? Molecular weight of solute, that is sodium hydroxide, is how much? Say students. It is 40. How it is 40? Atomic weight of sodium is 23. Atomic weight of oxygen is 16. Atomic weight of hydrogen is 1. Then see students. 16 plus 1, 17 plus 23 is equal to 40. Now, can we use this formula here? See students. Molarity therefore is equal to, weight is how much? How much it is? 4 gram. By molecular mass is how much? 40. Into 1000. That is one of the conversion factor. Constant. Then divided by volume. If it is in ml, we take 500 ml. Here. If it is in ml, then only 1000 will come. If it is in liter, see in the numerator, only 1 is there. So this 1000 factor comes only when the volume of the solution or solvent given is in terms of milliliter. Clear? Okay. Then how much it is? See students, this is 2. Then this is 10. This is 2 by 10. It means that it is 0.2 molar. It means that when you dissolve 4 gram of sodium hydroxide in 500 ml of water, the molarity of the solution obtained is 0.2 molar. Clear? Let us take another example. Say 4.9 gram of sulfuric acid is dissolved in 10 liter water. Then its molarity is how much? So the question is 4.9 gram of sulfuric acid is dissolved in 10 liter water. Then the molarity of the solution is how much? See, yes, the molarity of the solution can be calculated as N is equal to, this is the formula, weight by molecular weight into, see students, volume of the solvent is given in terms of liter. Therefore, it should be 1 divided by volume in liter. Is that clear? Now, what is its molecular weight? See students, hydrogen is 1 into how many times? 2 plus, see students, sum of the atomic masses must be equal to molecular mass. So here you should add plus. Here it is into, but here it is plus. Don't get confused here. Then atomic mass of sulfur is 32 into how much? How many times? It's 1 time. Plus atomic mass of oxygen is how much? It is 16 into how much? 4 times. 4. And you add all these, you will get 28. That means molecular mass of sulfuric acid is 98. Then what do we want? Weight we have, which is 4.9. Got that. Molecular weight is 98 into 1 divided by 10 liter is given. See you. 49 2s are 98. It's 4.9. That means it is 20. Clear? 20. That means it is. We can write it as 1 by 2 into 10 raised to minus 2. Because this is 2 into 10. This is 10. It means it is 10 to the power 2. 10 to the power 2, if you go to the numerator, it will become 10 raised to minus 2. This is 0.5. This is 0.5 into 10 raised to minus 2. Or we can write it as 5 into 10 raised to minus 3. Is its molarity. Yes, students? Molarity of this means that 5 into 10 raised to minus 3 molar will be the molarity of the 4.9 gram of sulfuric acid dissolved in 10 liter water. Is it clear? Okay. Then we take another parameter, another way of expressing this kind of solution. That is molarity. Molarity is represented by a small m. Okay. This is defined as number of gram mole of a solute. See, up to this, it remains same as with respect to molarity. Number of gram mole of a solute dissolved in 1 kg or 1000 gram of salt. This is very important. Here, solvent is expressed in terms of weight. In molarity, quantity of solvent is expressed in terms of volume. This is the difference. And see students, with respect to temperature variation, whether weight undergoes change or volume changes. Between weight and volume, which one will undergo change if you increase the temperature? See students, if you increase the temperature, what happens? Volume will decrease because evaporation takes place. When evaporation takes place, look at this. Molarity is mole by volume. If temperature is increased, what happens? Volume will decrease. Then the ratio will increase because denominator is decreased. That means ratio will increase. It means molarity will increase. That means temperature is directly proportional to molarity. If you increase temperature, molarity will increase. Molarity will increase not because of increase in the quantity of the solute, but decrease in the quantity of the solvent. Is that clear? I repeat. Increase in temperature decreases the volume of the solvent, increases the number of mole per liter. That's why molarity will increase, and hence molarity is directly proportional to temperature. That is, increase in temperature increases molarity. Next, what is the effect of temperature variation on the quantity of weight? There is no effect. There is no effect of change in the temperature on the quantity of the solute. When there is no, see here, molarity is mole by weight of solute. Molarity is mole by weight of solvent. And if you change the temperature, there is no effect of change in the weight. Change in temperature will not bring about any change in the quantity of the weight of the solvent, and hence molarity do not change. Yes, students, this is one of the important questions. Which one will get affected by changing the temperature? Means molarity only, not molality. This is molality. So molarity will not get affected by changing temperature. Only molarity will get affected by changing temperature, because molarity deals with quantity of solvent as volume, whereas molality deals with quantity of the solvent in terms of mass. Mass will not change with the temperature. Therefore, which is important unit to express the strength of the solution? Usually, molarity is preferred to molarity. Clear, students? Because of this reason. Okay. So this question may come in between molality and molarity. Which is the better unit to express the strength of the solution? What will be your answer? Okay, it should be molarity. Reason, mention the reason. Because molarity deals with weight of the solvent, which will not change with temperature, whereas molarity deals with volume of the solvent, which will decrease with rise in temperature. Hence, molarity is the better way, because its concentration remains constant for over a length of period. Clear? Therefore, from this, molarity can be written as number of gram mole of the solute by weight of solvent in kg. Clear? Now, this can be written as weight. Gram mole is weight divided by molecular weight. Molecular weight into 1 divided by weight of the solvent. Weight of solvent in kg. See, so there are two W's. Therefore, to distinguish between solute and the solvent, what we do is this we call it as 1, this we call it as 2. See here, always 1 or A indicates solvent, and 2 or B implies solute. Remember this. Then this can also be written as weight of the solute, that is W2 divided by molecular weight of the solute, that is solute only. See, I'm going to write molecular weight 2 into 1000 factor will come if weight of the solute expressed in terms of gram. This is molarity. Here, see, so we'll take one example. Suppose 18 gram of glucose is dissolved in 100 gram of solvent, 100 gram of say water, 100 gram of water. Then what is its molarity? So molarity, as we know that it deals with this weight of the solute divided by molecular weight of the solute into 1000 divided by weight of this solvent in gram, or 1 by solvent in kg. Here solvent is given in terms of gram. Therefore, it should be 1000 here. That means weight. Weight is how much? 18. Divided by glucose. Glucose is C6H12O6. See, this is 12 into 6 for carbon plus 1 into 12 for hydrogen plus 16 into 6 for oxygen. If you add all these, you get 180. That means molecular mass of glucose is 180 into 100 divided by this 1000 divided by 100 weight of, which is the weight of solvent. Then how much? 6 months. It will be 1 molar, because this is 10. 10 into 18 is 180. That 180. That means 180 divided by 180 is 1. So this means that when you dissolve 18 gram of glucose in 100 gram of water, the molarity of the solution is 1. Is it clear? Okay. Then we take another example. Another way of expressing the strength of the solution, which is mole fraction. It is represented by H. See, students, this is one of the most important parameters with respect to this particular chapter, because whatever we discuss in this particular chapter further, most of the time we use this. Therefore, it is very much important. If you have any doubts, please WhatsApp me that out. Okay. See here, mole fraction. This mole fraction itself indicates what it is. See here, it is fraction of a solute out of total moles. Its meaning is this. This implies that mole fraction is nothing but fraction of a solute out of total moles. This total moles means with moles of solution. See, students, fraction stands for division, isn't it? One important factor that you need to remember is, this is very much important. This concept is applicable for only for non-reacting substances. Chemically, non-reacting stands for chemically or chemical change should not take place, should not occur. When two or more substances are mixed, then chemical change should not occur. That means they should not react. Well, it reminds me one of the gas law. Can you guess it? Gas law. Total pressure is sum of pressure of all gases. What is that? Dalton's law of partial pressure. That means that Dalton's law of partial pressure also deals with mixture of gases, mixture of non-reacting gases. That means Dalton's law and mole fraction have one common feature between them. What is that? Both are applicable for only non-reacting substances or non-reacting system. Is it clear? Okay. Can it be one of the important points? Okay. Yes, it is one of the important points. Now, let us take one example and understand what it is. See, students, if A and B only are mixed, then we know that this system is binary. If A and B and C are mixed, we know that it is tertiary or ternary. If A and B and C and D are mixed, then we call it as quaternary, and so on. But for our syllabus, we have only binary system. It means only two components are mixed. And in that case, what we notice is most important factor to remember is mole fraction of A plus mole fraction of B will be always equal to 1. It also means that, see here, mole fraction of A plus mole fraction of B plus mole fraction of C plus mole fraction, sum of the mole fraction of N will be always equal to 1. That means sum of the mole fraction of any number of components will be always found equal to 1. This you should remember. It's very much important. As this concept is applicable for only binary system with respect to our syllabus, we go with respect to only that concept. Okay. Let us take one example. Calcium carbonate and calcium hydroxide are mixed. Okay, to make understand the concept in a simple manner, see, I take these required weights. See here, the molecular weights are like this. This is atomic weight is 40, this is carbon is 12, this is 16 into 3. This total will be 100. Well, this is 40 plus oxygen is 16 plus 1 into 2. Well, this is total, if we see here, this will be 17 into 24. This will be 74. That means molecular mass of calcium carbonate is 100. Molecular mass of calcium hydroxide is 74. These two are non-reacting system. Then why they are non-reacting system? Because both are alkaline or basic in nature. It means that this system is applicable for either acid and acid mixture or base and base mixture, but not for acid and base mixture. It's not applicable. So this is one of the important factors. They may ask you like this: for which of the following the concept of mole fraction is not applicable, or for which of the following the concept of mole fraction is applicable. Then in either of these two situations, your point of finding out is you should find out the choice where this holds good. If the question tag is for applicable, mole fraction is applicable, then you should look at any of these two. And if it is the question tag is not applicable, that means mole fraction is not applicable. In that case, this should be the answer. Clear? Okay. Then suppose we take weight as say 10 gram and 7.4 gram. This means we have taken 10 gram of limestone and 10 gram of calcium hydroxide. Then their moles will be equal to weight divided by molecular weight. So it will be 10 divided by 100. This will be 0.1. Then this will be 7.4 divided by 74. This will be 0.1. That means number of moles are 0.1 each. Then total mole will be equal to, this is 0.1 plus this is 0.1. Therefore, total mole will be 0.2. Okay? Then mole fraction of CaCO3 is equal to, this is mole fraction of CaCO3 is number of moles of CaCO3 divided by number of mole of CaCO3 plus number of mole of CaOH twice. Same things. What I said, mole fraction is fraction of solute out of total moles of the solution. We can write in this manner. What is this? This is number of mole of solute in this case now. That way, this will be solution total moles. That's why number of moles of CaCO3 is how much? What is this? 0.1. That way, number of mole of CaCO3 is 0.1 plus number of mole of calcium hydroxide is 0.1. Or we can write directly as 0.2. That means 0.1 divided by 0.2. It will be 1 by 2. This will be 0.5. So, mole fraction of calcium carbonate in this mixture, there is mixture of calcium carbonate and calcium hydroxide, where 10 gram of calcium carbonate is taken and 7.4 gram of calcium hydroxide is taken. That means mole fraction of calcium carbonate is how much? 0.5. Now, we can calculate mole fraction of calcium hydroxide as, see students, we know that mole fraction of calcium hydroxide plus mole fraction of calcium carbonate is 1. Just now I said, sum of the mole fraction of all the components will be equal to 1. Here, 2 components are there. That means, what is this? This indicates that mole fraction of calcium hydroxide will be equal to 1 minus mole fraction of calcium carbonate. How much it is? 1 minus 0.5, or it can be 0.5. Clear? Now look at this. Sum of these will be 1 only. Or there is another way of calculating. The usual way of calculating is this. See, so mole fraction of CaOH twice is number of mole of CaOH twice divided by number of mole of CaOH twice plus number of mole of CaCO2. This is equal to, we notice that how much it is? Number of mole of CaOH twice was 0.1 divided by 0.1, and this is also 0.1. This is 1 divided by 0.1 divided by 0.2, or this is 1 by 2, or this is once again 0.1. So either you calculate the mole fraction of the remaining substance, either as usual method or by this method. Sum of the mole fraction is always equal to 1. Is it clear? Okay. So we have discussed how many ways of expressing the strength of the solutions. One is mass percentage, then volume percentage, then mass by volume percentage, then molarity, then mole fraction. Then what is left over? One more thing that is left over is ppm, parts per million. Okay? Let us see that. See, students. Parts per million. Okay, let me write like this manner. Parts of solute per million parts of solution. Are you getting this? This can be written as parts of solute per million parts of solution. See, sir, per million, million stands for 10 raised to 6, that is 10 lakh. 10 lakh is 1 million. Okay. Then here ppm therefore can be regarded as parts of solute divided by total parts of all the solvents put together, that is solution, into 10 raised to 6. This is the definition. What is parts per million means? That itself, the name itself indicates number of parts of the solute present per million part of the solution is parts per million. Okay. Here, this part stands for either weight or volume or just a number. And this is used for expressing the strength of trace quantities of solution or solute. That means if the quantity of the solute is very much little in the solution, then we use this. Okay? We take one example. Then it will be very clear. See, so please. Say 10 milligram of calcium ions are found in 100 gram of water. Then what is its ppm? ppm of express this concentration of calcium ions in ppm. Okay, so here the units of one thing what we have to remember is the units in which solute is expressed, that must be the unit of solvent. Clear? Oh, let's see this. ppm is equal to, this is 10 milligram. Solute is 10 milligram. Solvent is 100 gram into 10 raised to 6. You have to equate the units. What is this? 10. Either you convert this into gram or you convert this into milligram. What do you want to do? Okay, I would like to go for this. 10 into 1000 gram divided by 100 gram. This is not 1000, it will be 6. 10 milligram divided by 100 into 1000 milligram into 10 raised to 6. I have converted gram to milligram by multiplying 1000. Okay, then how much it is? Here, 1010 get cancels. Right? How many zeros are left? 3 plus 1, 4. That means 1 divided by, this is 10 raised to 4 into 10 raised to 6. So here, this will be 10 raised to 6. When you take it to numerator, it will be 4. It means minus 4. This will be 10 raised to 2. This means this implies that this is 100 ppm. Clear, students? 10 milligram of calcium ions are found in 100 gram of water. It means in terms of ppm as 100 ppm. Clear? Remember that this concept is applicable for only trace quantities of the substances. Okay. In the next classes, we take some more examples of this and proceed for the next classes. Okay. And so one more thing is, as you have referred to the timetable, it is designed like this. 2 days, 2 subjects. Third day will be examination in theory as well as objective type on the third day. So tomorrow you will be writing examination on physics as well as chemistry, both theory as well as objective. Okay. Okay. Get ready for that. And if any queries are there, please WhatsApp that message. Immediately we will be trying to answer it. And we have prepared notes, handwritten notes, that we will be uploading it. Okay. Bye.